This is our solution to the philosopher assignment. So at the top we have define max hunger, which is the threshold of hunger that if the philosopher reaches that number, he dies. Then we have our struct, which is the ID, which is the number of the philosopher. We have the hunger of the philosopher and if he's eating. And then down here, the int is the number of philosophers, and the
Okay, that. Okay, and we have the p-tech and u-tech fork, which is this is used for the left and right fork, which will simulate the processes that we need for well, it will simulate the resources that each of these processes will use, and it will require the philosopher to have both forks in order to be able to eat, in order to simulate deadlock, and how these two processes are going to be using two different resources.
this takes the void arg argument and allows it in the think thread. It takes the void arg argument and allows it to access the philosopher struct. And then while the loop is true, it checks if the philosopher is eating, and if he's not eating, then the hunger goes up by 10. And then if the philosopher reaches the threshold of hunger, he will die, and text will appear stating which philosopher has died, and then the program will exit. And if the threshold is not met, then the philosopher ID is shown and it displays what hunger the philosopher is at. And then the sleep simulates the thinking time of the philosopher.
And here we have the eating thread. This takes the void arg argument, which is used to just ask the philosopher that's currently using the thread. And here we have the left fork, which take the ID of the first of the philosopher to simulate which fork the philosopher will use. So this will, like, it will say this will use the philosopher 0 will use fork 1, and philosopher 1 will use fork 1, so it will just use the current philosopher ID as the left fork. And the right fork will calculate the ID for the right fork, this over here. So it will take the philosopher ID added by 1, and it will do a module with the number n, so the number of the philosopher. And this ensures that if the philosopher is the last one, this module operator, it will ensure if the philosopher is the last one, it will wrap around and use fork 0. And yeah, and this ensures that, yeah, and that's so while this is true, the p-tech mu-tech lock, it would lock up both forks, so the resources will be locked up, this being the forks. It will try to pick up the left one and the right one, and it requires both in order for this program to run. So if both are capable of being used, it will go straight into eating. So it will say eating equals 1, so it says eating to true, and it sets the philosopher hunger to 0, so it resets the hunger after eating, and it print the idea of the philosopher that currently eating and the hunger that it's at by accessing the struct variable. And this simulates the eating time for the philosopher, and this just releases the fork, so it unlocks the right and left fork, so the another thread or another philosopher can use the forks. And then this sets the eating to 0, so false, so it simulates that the philosopher is done eating, and this simulates the time before thinking again, and this argument returns null. So here we have our main function, and first it prints how many philosophers are eating, so it actually uses how many philosophers are going to eat, and it records that number here. Well, it records the user input here, and here it assigns memory for So it will allocate memory for the philosopher. So it will take the number of the philosopher from the user's response and the size of the struct of the philosopher and assign it to this variable. And it will do the same thing for fork. The difference is that it takes the pthread mutex for the size of it and the number of the philosopher that it was inserted by the user and assign it a memory. Well, it allocates memory for it. And here we have the pthread this create the threads using the allocated memory for each thread. And here we initialize each philosopher in a for loop where it will continue going to the number that the user assigned, and it will go through every variable for the philosopher, assigning them variables. So this one over here assigned the ID, this one the hunger, and this one is set eating to false by default. And this is the pthread. This initializes the fork mutex, and this create the thinking thread and the eating thread for every philosopher.
This for loop makes the above threads actually run, and it only exits if a philosopher dies, in which case the program exits. And then these down here is what frees up the memory from the previous statements.
And it ends the program too.
So now we're going to run the program and see how it works.
Oh. Hold on, I need to reset it. I need to kill it. Okay.
Alright.
So we're running the program.
Alright, so we have to enter how many philosophers are eating. We'll say 6. And so now what the program is doing is counting up by 10. And you'll notice as it keeps going, it never gets above 70 because the correct memories are. So when it gets to 70, they begin to eat so that the philosophers never get close to the max hunger.
And you can see, like, it just keeps on running, so that means that no deadlock is actually ever close to happening due to it not even coming close to the max hunger. So this program will keep on running forever until we kill it. So yeah, this shows that there's no deadlocking. Every resource is being freed at the right time, and yeah, this just solves the philosopher problem. Right.
Yep.
So
this was our solution to the problem, and thank you for watching.
all right.